Convergent equilibrium point. Now another property of what? Of equilibria. So we are not talking about a system. We are talking about a single equilibrium of the system. Okay? Convergence. Let's go here. Why is this one different than this one? Here we lose energy, true? So in a certain sense, we fall back to the equilibrium. Here, we do not fall back, true? You see that in a certain, the convergence thingy already has a name, suggests you, if starting somewhere kind of makes you go back to the original equilibrium point that you were thinking, true? For example, if I've got an ODE that looks like this ODE, y dot, I have convergence towards 0, true? But if I've got an ODE that looks like 0, here I do not have convergence. If I start here, we remain here. If I start here, we remain here. True? Perfect. So, convergence is this property here. Where does the system end up if I start sufficiently close by? Okay? So, definition in continuous time. We have constant u, we have our ODE with a constant u, and we have an equilibrium. For example, this one. YE is convergent if there exists a neighborhood containing that equilibrium, a delta ball around the equilibrium, such that if one starts from within that neighborhood, if I start inside here, I am guaranteed that I go there at the end of time. Okay? Let's see it. Here, in this case, do we have convergence? Yes. In this case, do we have convergence? No. In this case, do we have convergence? Yes, because we are able to find a small enough set for which we have convergence. Okay? Together? This one, do we have convergence? No, because there exists at least one trajectory that brings me away. Together? This one, do we have convergence? Yes, no, I do not know, discuss. What do you say, people? What would you say? 1, 2, 3. Convergence is there exists a ball around the equilibrium. This means there exists a ball around the equilibrium such that if I start inside here, anywhere inside there, then I know that at the end of time, I go back to the equilibrium. True? Does it hold here? Yes, very much. True? Together? So this one is convergent. Was it marginally stable? No. Very common mistake. blend the two things into one thingy. They are distinct properties. We are going to come back very soon on this. Okay? Very soon we are going to come back. This is an example for which we have convergence, we do not have marginal stability. Okay? There will be cases for which we have marginal stability and we do not have convergence. There will be cases for which we do not have both. There will be cases for which we have both. Okay? All four cases might apply. Together? Perfect. Watch out, because the two things are two slightly different viewpoints. Eventually, this means simple stability. Read this. Read this. Think 1 minute about this sentence here highlighted. You see that somehow this epsilon that the boss chooses, delta that you choose is, I can confine arbitrarily the trajectories wherever I want. Whenever an equilibrium is marginally stable, in a certain sense, I can confine the trajectories by choosing a delta that is sufficiently small. True? Does this definition say something about the end time? No. If I've got something like Lotka Volterra that does this all the time, I can confine my trajectories. It doesn't tell me anything about where it ends up at the end of time. Are we together, people? 1, 2, 3. Tell me in case it's not clear. Are there questions about this? Yes.
It was the, I didn't pay attention. It was the simply stable equilibrium that you just explained.
Lotka Volterra. How does Lotka Volterra look like? It's something like this. Trajectories that look like this, true? And if you start here, you go on all the time in this way, true? Are you able to confine the trajectories from here? If I choose a very small delta, in a certain sense, I stay there. So if somebody says, are you able to find a certain delta such that you stay inside this, a certain epsilon? For any epsilon, I'm going to be able to find a delta sufficiently small. True? But this doesn't tell you where you end up. This one, does it tell you something about what happens in the transitorium, in the transient? No. It tells you what happens at the end. So, like this one, things might go astray, but the convergence is what happens at t equals infinity in a certain sense. Okay? Together? So, they are two definitions that, in a certain sense, from a time perspective, they focus on different objects. Okay? This is interesting. And this we do it together. I have this system here for which, how do the trajectories look like? Up to a certain time, I've got divergence. True? And at a certain point, I have convergence. This is a switched system in the sense that it switches at a certain specific time from one behavior to another behavior. How does it look like? T, y of t, let's put 10 to the power of 5. If I start here, I will do like this, and then I will do like this. True? And if I start here, I will do something like this, and then I will do something like this. True? Together? Perfect. This one, if I start in 0, what do I get as a trajectory? 0. True? So this is an equilibrium. 0 is an equilibrium. Are we together? So we can talk about convergence properties and simple stability properties of equilibria. We cannot talk about the convergence properties of this stuff here. This is not an equilibrium. Are we together? So about 0. What is it? Table by table, discuss. Let's see. Start with discussing convergence. Do you think it's convergent? Yes or no? No. Okay, look at me, look at me, look at me, look at me. Convergence. For convergence, are we talking about something that happens at the end of time or something that happens here? At the end of time, true? So convergence is eventually, do we go back? True? This is the question, convergence. True? Okay, continue the discussion. So, yes, it is convergent. No, it is not convergent. I do not know. Let's go three. Let's go here. Convergent, not convergent. I do not know. What would you say? I see some few people that say not convergent. Why not convergent? It is convergent. You start, if you take this delta, true, you're gonna go into, at the end of time, into zero, true? And also this delta is okay, and also this delta is okay. There exists a neighborhood of the equilibrium such that starting that neighborhood, eventually you fall back into the equilibrium. Do you see it? Are we together, people? I don't care if at a certain point I go out of the neighborhood and I go back. Let's go back here. Where was it? Here. Isn't it the same? I take this delta, starting inside here, I will do some trajectories, but I know that starting inside there guarantees me that at the end of time I fall back there. Are we together? Question. That's a question there. Question.
I was just thinking, you said the end of time.
Hmm.
You know it will end up in the middle. If we would check sign, you don't know where it ends up.
But as a sine function, if a function does like this, if the trajectory does like this, would it be convergent? No, perfect. Are we together? This ODE that has got this type of behavior, the origin, is it convergent? Yes. Are we together, people? Is it marginally stable? Is it marginally stable? Discuss. Marginally stable? Yes. No. I do not know. So, what would you say, people? What would you say? No, no, yes. How, that, answer. I really would like to see this one. Somebody that says no, may somebody that says no come here and play the boss? Come, come. You play the boss. You've got to select an epsilon, and I've got to select the delta.
Yeah.
True?
I would select like in zero, like here.
No, the epsilon has to be bigger than zero.
Yeah, because just yeah, I lose. I'm losing.
You're gonna lose. Look at me. Well, is there a question? Sorry? Look at me. Let's pretend I do the boss of myself. I choose this epsilon here. Okay, this is the epsilon ball. Okay, it's a one-dimensional ball. True? Because the set of initial conditions is on a line. Okay, so the sphere, the hypersphere, is actually a segment. Together, this is my epsilon. Look at the operation that I do. Perfect. This is my epsilon. Then it means that I have this epsilon also here. True? Perfect. Then I trace back the trajectories. Here, I think at which initial condition do I have that takes me here? And then I take this one as delta. True? True? And if I start inside delta, I will have trajectories that are going to stay inside epsilon. You see? That delta might be very small, depending on the epsilon. And the bigger this 10 to the power of 5 is, of course, the smaller delta I need for any epsilon. You see it? But are you seeing that for any epsilon that you choose, I'm able to find a delta such that if I start in delta, I will stay in epsilon. Do you see? Are we together that this is marginally stable? How much are we together, people? 1, 2, 3. Perfect. Now you do this exercise. Go. Look at this. This is slightly different. Look at me. Look at me. This is, I have +1 until the trajectory hits 1 in modulus. Okay? The timing for the switching is not depending anymore on t, it's depending on the trajectory itself. Might happen, there might be systems like this. What does it mean? That from a time perspective, when will the switching happen? Whenever I have 1, whenever I touch 1, then I will go down. If I start here, I will go down. Whenever I start here, I will go down like this. You see it? Are we together? Do we have convergence? Yes, no, I do not know. Discuss if there's convergence. Zero is again an equilibrium. True? Zero is again an equilibrium. So the convergence of zero, is zero a convergent equilibrium? People, may you answer. This one should be, I hope, clear. Do we go back to 0? Yes, we have a neighborhood such that starting that neighborhood, eventually we go to 0. So this is convergent. True? Are we together that it's convergent? Perfect. Is it marginally stable? Discuss about it. So, people, what would you say? What would you say, people? I would like everybody to answer. No, why? Because if the boss says this is your epsilon, choose a delta, you are not going to be able to find a delta. You see? Why? And it's because the switching makes your trajectory go to 1. Okay. So independent of the delta that you choose, you are going to go up to 1. This is the point. The main difference with before is that here, by choosing something that is small enough, I can make this peak small enough. Here, whatever I choose here, delta bigger than 0, of course, I need to have some meat. Okay, it's not, you cannot choose a radius equal to 0. It's not a ball anymore. Together? The fact that I've got a switching that switches on a certain value and not on a certain time makes me unable to confine the trajectories where I want. Together? Convergent, not marginally stable. Convergent and marginally stable. Okay? Together? That's it. We should be there. So people, what would you say? Everybody answers 2. Excellent. Almost everybody says 2. Convergence is what happens to t that goes to plus infinity. Stability means, am I able to confine the trajectories? Okay. If I have trajectories that look like this one, etc., like a sine, that ones are gonna be not convergent because they don't converge, true? But they are gonna be stable. Lotka Volterra. Lotka Volterra is an example, true? Lotka Volterra is an example. You see that Lotka Volterra is an example of something that is not convergent, but also stable, simply stable. Okay? We are together, true? Perfect. Are there questions on this part?